Right. Okay, good morning, students, and we are on to mathematics once again for grade 10. Today, we are continuing our logic reasoning series by looking at compound statements. But before we go into compound statements, let's have a brief overview of the assignment, and then we'll then build on that. Our textbooks of reference would be the New General Mathematics book for SS1 and the Excellence in Mathematics for grade 10 or SS1. All right. So with that in place, you can turn, if you're using the old edition, it will be on page 107 for that. And then if you are privileged to have the other one, which is Excellence in Mathematics, that chapter can be found in a topic where that will be found in page 176. So I'll just have the put down so that if I have need to make reference to them, I can just quickly do that. So I'm back to my New General Mathematics, and in exercise 9b says write negation of the following statements. I think we've treated this. In our last class, so we would proceed. We've also done 9c, all right? So we go straight ahead to compound statements. Now, the concept of compound statement is putting two simple statements together. Come again. The concept of compound statements is putting two simple statements together. Putting two simple statements together gives us a compound statement. Okay, now if you look at, for instance, we have a set of what? Students who are in SS1. Now, for students who are in SS1, there are different possibilities we can have. We can have students in SS1 who are offering specific subjects. Like if I pick physics, for instance, I could have students who are offering physics, and I could have students who are what? Offering what? Who are not offering physics. So a compound statement would usually have other sub-statements. To understand a compound statement, we imagine the universal set. To understand a compound statement, we imagine the universal set. We had said that the universal set is the largest possibility in any set question. So the compound statement is the what? Is like the universal set in this context. And then we have sub-statements in it. We have what's called sub-statements. Those sub-statements can now represent various sets, subsets, as it were, subsets, as it were, of these particular sets. All right. So if that understanding is gotten, if we take a particular case scenario we were talking about, like the case of physics. If in a class we are considering students who are in that class as the universal, it means we can say those who are offering physics will be in here, and those who are not offering physics will be out here. So that brings us to the statement and the negation. So the negation plus the statement, or the original statement, gives us the compound statement, or as it were, the universal set. Do we understand that? If I say P students offering physics, it means that P prime will be what? Students not offering what? Physics. That's what it will mean. So these are two iterations of the compound statement or the universal set. So take home, the universal set is like the compound statement, where the negation and the statement itself, the negation of the statement and the statement will make up that compound statement. Having understood the compound statement, the next thing we may want to talk about is what is called the implication. Implication. Is the implication. Okay, before we go into that, let's look at what our excellence in maths has to say about compound statements. Now, it says in everyday life we do not communicate with what simple statements, and that is true. Our statements in communication are actually compound. We use specific words to combine simple statements, depending on the meaning we desire to convey. It is raining and the wind is blowing. There's an apple or banana in my lunch bag. If I study hard, then I will pass exams. So these are variations of what? Compound statements. I just use this one as one case study for that. Now, in looking at compound statements, there are, maybe I should treat that one first before I go into implications and the likes. In looking at compound statements, there are certain things you must take into consideration. So in looking at compound statements, there are 5 connectors. 5 connectors we will need to take note of. There's one called this, there's one like this, there's one like this, there's another like this, and there's another like this. So these are 5 connector symbols you must know to be able to deal with compound statements in what? Logical reasoning. The first one is the one we call complements. You are already used to that one. The second one is the one we call intersection. You're already used to that already. Intersection in bracket and. The next one is what we call union. You are used to that one already. What we call or. In set, it was this symbol. But in logical reasoning, these are the symbols we use. Sometimes, even in logical reasoning, we can still use this. It's still allowed. The next one we will look at is the one we call conditional. It's called what? Conditional. And let me write the implication of this. If I consider 2 sets, for this it will be simply like this or this. For this one it will be something like this: A intersection B. For this one it will be what? A union B. For condition it will be P. P condition Q. Where in this case it means that Q contains P, or P is contained in Q. Remember that we treated something like that earlier. Contained is said being contained in another and things like that. So this is that for that. So it means that the concept at here is subset. This B is a subset of Q. So I can write that P is a subset of Q. Let's get that. We're working with our background knowledge of sets. Now, the other one is what we call biconditional. There's conditional and there's also what they call biconditional. In biconditional, we have that P is exactly equal to Q, and that is the one they call equality set. Equality of sets. Equality of a set. So it means that everything I have here is exactly what I have in this place too. I hope that is clear. So please, let's take note of all of this as we proceed. Okay, so let's start with the first one. Now let's look at an example here. There's an exercise here. Okay, before we go into that, let's start with the first one. The one is called logic. Please, let's watch this. Meaning, it's supposed to be what I had done before, but let me put it properly so that this is for logic, meaning and symbols and meaning. Is that clear? Then we have what is called set. This is logic. This is set theory. And this is what? Symbol. Let's draw the table out. Let's draw this table out. Now, you discover that there's a relationship between logic and set theory. Sometimes in problems, we use them interchangeably. So this is what? P prime, which will mean not P. In set theory, we call it P prime. This is P prime. This is P, what do you call it now? P complement. P complement or P prime. So that settles that. Then the meaning is what? Is complement. So here it is complement. Here it is not P. Logic, this one means not P. If you remember the first class we had, this is not P. We said there were three symbols we used in that class. We use this, we use this, we use this. I would say they all mean the same. This is P bar or bar P, just to help you, bar P. This is not P. This is P complement. So take note of that, just to help you remember that. Now the next one is what? P. This is how we write it in sets, and this is called a conjunction. Now it will interest you that we are studying a bit of English in sets. In fact, it's essentially English. Conjunction. A conjunction is a word that connects. Conjunctions usually connect. So if I say and is a conjunction. So this would, they are connecting words. So this would be what? P union Q, and that is what? Intersection. We'll get to understand conditions for which all of this will work out. Please take this topic very seriously. The next one is P, something like V, Q, and that is what? That is what we call disjunction. Disjunction. That is more like, disjunction is like or. If this one, any of them, if any of them works, it is correct. So this will be P. Oh, sorry, I missed it here. Please, sorry about that. Intersection, sorry about that. I missed the sign. And this is union. The next one is called P. This is what they call P implied Q. It's what they call conditional, or what is called conditional. It's a conditional statement, and it means P is a subset of Q. So the concept here is what? Subsets. And the final one is what we call the equality of set, where P is what is called biconditional. P biconditional Q, here is biconditional. P equal to Q. And that will be equality. Equality. So that's equality. So these are the logical implication and then the set theory. Please take note of this. You must know this. It's so important because a lot of things I'll be saying later will revolve around these things. So I'll pause. Conjunction. Conjunction is statements that are connected by words and. So two simple statements are joined by words and. So in conjunction, two simple statements are connected by and. Two simple statements are connected by and. So for this statement, for this type, the outcome is only true, or the outcome is true if both statements are true. You need to write a lot now. Please, this is not the time to sit down and watch. You really need to be writing. It's a very sensitive aspect of maths. Two simple statements are connected by what? And. For this type, the outcome is true if both statements are true. Now, there's what we call the concept of truth table. So now, a truth table is used in logic to show the possible outcome, or to show the possible outcomes. How is it being done? Look at it. This is what a truth table look like. For this scenario, you have P, you have Q, you have P and Q. So remember, for conjunction, this is the symbol, and. And we have said that for any statement to be true, for the outcome to be true. Now this is the outcome. This will be the outcome. So these are the possibilities. Is either this is true, this can be true, true, false, false, or this is true, this is false, this is true, and this is false. Those are the possible outcomes. So both of them are true. This will be true. Remember we said that the only way this can occur is if we have what? Both of them are true. So for all of these ones remaining here, it will be false. The outcome can only be true if this is true and this is true. Look at this very well, because you also meet it again in further maths. And for those of us who are going in to study electrical electronics engineering, or those who delve into software computer, this will be your this will be what you will see regularly. Your logic circuit designs are based on this. It takes you to an aspect of maths called Boolean algebra. So I'm just saying this because I see almost everybody here as a science student. So this information becomes very important for you. All right, so that is what is called the conjunction. In conjunction, both statements must be true for the outcome to be true. So after taking care of that, let's come to number 2, which is called disjunction. So two statements are connected by what? Or. Two statements are connected by or. That's it. In disjunction, two statements are connected by what? Or. For this type, comma, one of the statements must be true for the outcome to be true. You notice that as I'm talking, I'm writing. So if you miss it in terms of what I've written on the board, you can pick what I've said. Two statements are connected by what? Or. For this type, one of the statements must be true for the outcome to be true. So we're going to do a truth table here now. P, Q, and this is P or Q. So we take our possibilities again. Remember that we said that one of the statements must be true. If both of them are true, it will be true. If one is true, it will be true. If Q is true, it will be true. If both are false, the statement becomes false. So for all of disjunction, we expect both statements to be true for this theory to be upheld. So that's for the next one. For this one, let me show you in set diagram what it will look like. In set diagram, what this will look like. What does a conjunction look like in set diagram? It is intersection. This is P and this is Q. So in set diagram, it is intersection. Do you understand? So P intersection Q. Please take note of that. In set diagram, that's what it will look like. That's for this one. So I'm going to also prepare set diagram for the disjunction. Disjunction, comma, the set, the Venn diagram will be, for this one, the Venn diagram will be what? All the Venn diagram look like. It will be this. It will be all of this. So that is what? P union Q. I can ask you in a test. Use a Venn diagram, represent a disjunction with the Venn diagram and truth table. That's what I expect you to do. Venn diagram, truth table. So the truth table for this one is this. While the truth table for conjunction is this, with the Venn diagram being this. All right. We'll now come to what is called conditional statement. Conditional statement. So number 3, conditional statements. Conditional statements. Now, conditional statements. So what is that? A conditional, now take note of it. We have treated complex statements. So The first one was conjunction. Next one was disjunction. Now we're going to treat what is called conditional. Now, in a conditional statement, we usually will have something like P implies Q. So sometimes another name for a conditional statement is implication. So for a conditional statement is what? Implication. So in some books, you may not. Now, P implies Q. So P implies Q means what? Will mean that P is contained in Q, or Q, rather P is a subset of Q. So let's get that understanding right. Let's get that thing right. So in this arrangement, P is what is called the antecedent. P is what is called the antecedent, and Q is called the consequence. So P is the antecedent and Q is called the consequence. So let's look at our truth table, because I'll use my truth table now to explain. So truth table of implication of conditional statement. So let me prepare a truth table for that. So you have P, you have Q, you have P implies Q. So let's look at how that one works out. Now, true, true, false, false, true, false, true, false. Now, how does implication work there? Now, for implication, if both of them are true, it will be true. If this is false, this will still be true. If this is false and this is false, this will still be true. But if this is true and this is false, this will be false also. I know it's really very interesting. It's really very interesting how to explain this. Well, let me try to see if I can get an example to explain this. It can be very tricky for students to understand. Ako. Now look at this. Look at this. I think I just thought of a very interesting example for it. Look at this. A square is a quadrilateral. We know that a quadrilateral is a square. Which of them is correct? 1 or 2? And why? A square is a quadrilateral. Is it true? A quadrilateral is a square. Which of them is correct? You should see why it is conditional now. Waiting for feedback. Okay, let me, don't worry, let me unmute you so that you can.
Sir, if you go with the answer B and see that a quadrilateral is a square, you are wrong, because there are plenty of quadrilaterals which are not squares, like rectangle, parallelogram, kites.
Beautiful. Good. So you discover that this is why it's a conditional statement. A natural number is a real number, but a real number is not a natural number, which means that this is the container. This is it. So this is the content. This is the container. That's the concept of implication. So if this is true and this is true, this must be true. If this is true and this is false, it will be false. If this one is true and is not contained in this person here, it's useless. That's what's happening here. A quadrilateral is a square. No, it's not possible. A square can be a quadrilateral, but a quadrilateral can never be a square. So that's the understanding of implication. The condition is that this one, as long as these ones are true, as long as this one is true, Q is true, the statement must be true. If they are both false, the implication is that it is true. But if you have a situation where P is true and Q is false, no, the outcome will definitely be what? False. All right, so let's take that. That's for implication. So that's why we say it's a subset. So I'm going to represent that in a diagram. In set theory, it will look like this. It will look like this, where this is P and this is what? Q. Q and P. So P is contained in what? Q. So that's the summary of that. All right. All right, so let's have the last one. The last one is the one we call biconditional. This is what we call equality of sets. Biconditional. Biconditional statements. So what is it? What is biconditional? It is this is what it means. P. Okay, I didn't say something here. This one means if P, then Q. If P, then Q. That's for what do you call it? That was still under your conditional statements. So let's go to biconditional. To be so in this one, an outcome An outcome is true if both are true or both are false. So if both are true or both are false, the outcome will be true. So let's look at the truth table here. This equal set. The concept of equal set will help you do this. So true, true, false, false, true, false, true, false. Now, if both are true or both are false, you have true. If one of them is true, it will be false. So what's the biconditional? So it is P if what do you call it? It's P if and only P if and only Q. P if and only P if and only P if and only if Q. So both conditions must be satisfied. If both of them are true, the statement will be true. If both of them are false, the statement will be true also. If one is true and the other is false, the statement becomes false. I'm trying to think of if it's 5 naira. If you bring 5 naira, it's just like a simple example is like an equation. Left hand side must be equal to right hand side. If it's not that one, it's not correct. The item on the left hand must exactly balance out the item on the left hand side. So that's the narration that's playing out here. All right.